Recording is now in progress. All right, so we left off with the Steinitz exchange lemma. So this is a very classic lemma from the world of vector spaces. Already did my joke about Wilhelm Steinitz, who's Wilhelm Steinitz, who's not the Steinitz, is different Steinitz, the chess champion. This is just some math guy. Whose Wikipedia page is whose Wikipedia picture is a grave. Still can't get a like. There's nothing. There's no like portrait. Here's his tombstone. Anyways, this is a very famous result. It's called the exchange lemma because what it basically says is that if you're looking at a set that's been spanned by finitely many things, and you have finitely many linearly independent things, basically you can exchange a bunch of the elements that span it with the linearly independent elements instead. So you've got your things that span it, and then you can basically take the first thing and replace it with the first element from the linearly independent set. And then you can do this until you completely exhaust your linearly independent set. So note that the real power of the Steinitz exchange lemma is this conclusion right here. Right, and as we're going to see, once we have this proven and we start using it application-wise, we're going to see that the real power of this theorem is this conclusion right here. This other part is just sort of like nice, but as we'll see, it's kind of a non-constructive argument because it tells you that, well, there exists things you can replace W with, and the key thing being that it's the linearly independent things. But as we're going to see in the proof, what the U's are, you kind of don't really have control over them. And so, and I have to kind of call that like a non-constructive argument, like in a, there's no explicit way of explaining what these are. They exist. You can find them, I guess. But anyway, so the real power is this, because what is this saying? This tells me that if I am looking at a set that's been spanned by, say, 6 things, I cannot find 7 linearly independent things in that span. The number of linearly independent things in a set that's been spanned by finitely many can only ever be that amount. So, for example, in R4, we can't have a set with 5 linearly independent elements. Or, again, the way we talk about linear independence, we don't say it right? We can't find a set of 5 things that's linearly independent. Really. Right? And that's incredibly powerful. For a variety of reasons, as we'll see, it's going to tell us a lot about how we can construct bases in Rn. And once we get to matrices, which will be the end of next week, having that theorem ready to go is going to immediately tell us a lot about how matrices are going to behave, and thus tell us a lot about how solutions to systems of linear equations need to behave. And again, we're doing the book out of order, and the reason we're doing this is precisely that. If you prove all the stuff about vector spaces first, getting into matrices, you have all these big theorems. You basically have all these big guns to let you just anything you want to add question about matrices you want to answer. You got all the vector space stuff that you can just bring in and bing, bang, boom, theorems are done. So, yeah, it's the reason we decided to choose it this way. It does create, like I said last time, kind of an issue where right, we got some proofs that are going well outside of what the book does, but anyway. All right, so let's get to the proof of this. All right, and so as we noted, it's going to be an induction proof. So we'll prove the base case, and then we'll assume something is true, and then show that from that assumption you can move over to the next one. Yeah. So the first step is to prove that when j is equal to 1, the 2 conclusions hold. Right, and so our 2 conclusions are that the index is always less than m, and that I can always replace the w's with some u's, where the first j u's are taken from the linearly independent sets. Okay. All right, so last time we noted that, all right, well, when j is 1, that's definitely less than m is a positive integer, so that's free. V sub 1 is in the span, which means it's a linear combination of these w's. And it cannot be that all the scalars are 0. If that was the case, then V1 would have to be 0, but that can't possibly happen since it's coming from a linear set. Right? So that means there is some alpha sub j that's non-zero, and that's precisely what we're going to exchange. So the v sub 1 is going to basically replace wj, but we're going to re-index it so that it starts with v1. And that's what kind of makes this proof mildly irritating, in that there's just like kind of a lot of rearranging we're going to do. So it's going to be a lot of different symbols. But ultimately, just always keep in mind, we've got some set that's spanning it. We've got linearly independent elements inside of it. And we're always going to be able to find a spot where we can exchange that thing in the span with the linearly independent. All right, so since there is a scalar that is non-zero, we'll rearrange the w so that the first one is the w sub j. So the non-zero scalar is just the first term, right? Because we want to swap v1 with the first thing. So that we rearrange it so the non-zero scalar comes first. That means then that v1 is a linear combination of these z's, where we've got some betas, right? Because the z's are just a scrambling of the w's, so just move it around. And the main thing to note is that beta 1 is alpha sub j, right? And so then now we do the exchange. We'll subtract v1 over, subtract beta 1 z1 over, and then solve for z1. And that gives me this. So we exchange the first term with what it's equal to on the left. And now here we have these u's. These u's are a scrambling of the w, except that I threw out one of them and replaced it with v1. And the key thing to notice now is that, all right, all the z1 to zm, this has to be in the span of u1 to um, because for any k not equal to 1, you just have z's. And right, so the z's land in here, because right, the u's are just z's except for the first one, which is v1. So z2, z3, z4, so on and so forth are just trivially in here. z1, however, is still going to be in the span because we just demonstrated that it's equal to a linear combination of the u's. So you started with the w's, you scrambled them into the z's, and then we swapped to create the u's, where the u's are the w's that have been scrambled, and you remove the first one and replaced it with v1. So like I said, the main idea is not hard. It's you're finding a non-zero scalar, and that's what you're swapping. The problem is when you're writing this proof, there's a lot of like rearranging you have to do. There's a lot of extra symbols, so it's easy to get lost in the sauce. So we want to keep that in mind. You know, every little thing, remind ourselves of what's what and what's going on. Okay, so Z2 all the way up to ZM, those are just the UKs by definition, so they're obviously in the span. And Z1 can be written as linear combinations of the U's, so that means it's in there. The Z's are just the scrambling of the W's, so their span is the same. And now, since Z1 to ZM is in the span, that means the span of that is contained within it, because span is the smallest subspace. And however, the U1 to UM, if we think about what they are, well, the U1 is V1, which by hypothesis is in the span of W1 to WM. U2 are, and beyond, are just the Z's, which are equal to W's, so they're in the set. So that means the span of U1 to UM is the span of W1 to WM, right? Because we have subset in the forward direction, and this one ensures subset in the reverse direction. There we go. So we've proven, so let's recap what exactly we've proven. So we have proven that you have a set that's being spanned by finitely many things, W1, W2, all the way to WM. And now we've proven that basically you can throw one of those out and re-scramble it so that the first one is V1 and the rest are some W's, not necessarily W2, so on and so forth. They're just some W's. And the span remains the same. So we're able to exchange one of the W elements with V1. And then we rearrange it so it starts with V1. This is just for like convenience of stating the theorem. All right, so base case has been proven. So now it's the induction hypothesis phase. Okay, so now suppose that we've got J, it's between 1 and n minus 1. It's worth noting that this is an induction on just a finite set, so you prove it's true for the first one, and then you assume it's good for one less, because then we're going to prove that j plus 1 works. But if j is equal to n plus 1 isn't in the set, so it's can't. So when you're doing the induction, you need to point set. And this is very important because this actually will play a role in the proof. So this is potentially the first time you've seen an induction where you're restricting it to a finite set. The argument is still the same, but basically what you do is the hypothesis is there is a number that works that's one less than what we want. That will play a role here in a moment. Anyway, so we will assume there is a j between 1 and n minus 1 that works. So in other words, j is less than m. And there is a scrambling of the w's so that we still span the set, but the first couple of elements, the first j ones, are chosen from the linearly independent set. There's my dogs. Abby, Lily, put it. Good. It's fine. Don't worry. Go. No, don't. All right. Anyway, here they are. They want to be seen. Abby, Lily. Abby's the black lab, Lily's the yellow lab. And yes, Lily is overweight, and no, it's not going well trying to lose pounds. She got up to 130, and we got her back down to 120, so good. Yes, they are very good dogs. So yeah, we checked with Lily, like, because originally thought she had like a thyroid problem. She like ballooned up out of nowhere, and then all the blood work came back. Now she's just a fat dog.
Sometimes it happens when the dogs are castrated.
Yeah, they're both spayed. They're both. Yeah, apparently it happens sometimes. But I mean, Abby is fine. Abby's within healthy weight. Lily's really good at finding food. Hey, get out of here! I know I'm talking about you.
My cousin had a dog that looks like more like a bear than a dog. It's a brown lab, and
yeah,
it just looks like a bear.
Yeah. All right. Okay, so let's get to it. All right. So before we get to the proof, so hopefully we're all copacetic. We're on the same page here, kind of what's going to happen. Basically, the proof here is going to go exactly how the base case proof went. It's just going to be like mildly more involved. Because instead of just having the first term, there's now j terms that we have, and so there's going to be more indexing and scrambling nonsense. But the key idea is still there. V sub j lives in that span, so that means it can be written as a linear combination. And now specifically of the u1 to um's, we don't want to use the w's for this part here. Because the U's already have the V1 to Vj in there, so we want to use those to our advantage. Okay. So since the V sub j is in that span, there's a linear combination of it, and now here it's the same argument. All right. Well, if all of those scalars are 0, and now specifically, if all of the scalars beyond j are equal to 0, then that means V sub j is a linear combination. V sub j plus 1 is a linear combination, and that's a Vj must be a Vk. Like I said, this is just like a lot of indexing tomfoolery. Where's it fixed? There we go. That means V sub j plus 1 is a linear combination of V1 to Vj, but that's bogus. That's a linearly independent set. That can't happen. Because if you were to subtract this over, you've now got a non-trivial linear combination giving you you now have a trivial linear combination with non-trivial scalars. So cannot happen. Right. So that means that there has to be something between j plus 1 and m that the scalar is not equal to 0. Because if there isn't, that means all of those terms are gone, and we have the v sub j plus 1 as a linear combination of v1 to vj. We're fine. There's a graveyard in my backyard, and people are in there sometimes. trying to grieve, and then my dumb dogs are barking at them. Well, it doesn't seem to be anything over there right now. Anyway. Okay, so that means that there's got to be a P that lives strictly between J and M so that the scalar is non-zero. And note that immediately guarantees there's something between J plus 1 and M. So J plus 1 needs to be less than M. J plus 1 cannot exceed M. So there we go. First part of the hypothesis taken care of. And again, that's really the thing we really want. We really want that to be true. Because now, right, as we're going to go and finish the proof, we now have the main thing of, in a set that is spanned by finitely many things, there cannot be more linearly independent things than what had spanned the set. And that's really the powerful thing here. It's the main, the kicker of the Steinitz exchange lemma. All right, so we got to finish the proof, though, here. So what do we need to do? Well, we got to do more rearranging. And so what are we going to do? Well, there is a P strictly between J and M so that the scalar is non-zero. So rearrange it very specifically. Remember, the U1 to Uj are equal to V1, V2, all the way up to Vj. We want to keep that, so rearrange it so that the first J terms are the same, but now we've rearranged it so that the J plus 1 term is the term associated with the non-zero scalar, and then that's what we're going to exchange, and then so UP will be exchanged with V sub J plus 1, and that finishes the proof. And it's exactly the same as the base case argument, because here's what happens. So remember, V sub J plus 1 is a linear combination of the U's. This is just some scrambling of it. So it's still a linear combination. The only difference now is that we specifically know that the J plus 1 scalar is the non-zero scalar. Okay. And then now we swap the J plus 1 term with the Vj plus 1 term. And it's exactly the same as before, but instead of swapping out the first term, you swap out the J plus 1 term. And that's it. So again, we now arrive at another reindexing. So where the Y sub k's are some reindexing, where the Y sub k's are the X sub k's, but you've thrown out one of them. So the Y sub k's are all the X sub k's except for one. The X sub k's are all of these rearrangements of these U's, and these U's were guaranteed by the induction hypothesis. So a lot of junk to take track of. But note the key thing now, X sub J plus 1 is a linear combination of the Y's. So, finally, the X1s are all in the span of Y1 to Ym, because all of the Y's are X's except for one of them, and the one X that's not a Y is a linear combination of the Y's, so it has to be in there. By induction hypothesis, the span of W1 to Wm is the span of U1 to Um. X1 is a scrambling of that, so the span is still the same. Now the X1s live in the set, so that span is in there, and these Y1s, again, they're all X's, except for the one that is a V, but that lands in this span anyway, because that span is equal to this span, which by hypothesis is in. So all the Y1s are in there, and then all the spans are equal, and the proof is over. Did it. Hooray. All right. So that is easily going to be, I think, for some time now, probably the most labyrinthian proof. And again, it's not like it's hard to understand what's going on. It's basically like you're just making this linear combo. You know that there's a non-zero scalar, and then that's what we're going to swap with. That's what we're going to do the exchange with. It's just all the details. You have to do all these rearrangements, and so you're just like, you're taking a list, and you're creating a new list, and then you're creating a new list, and they all have the same span. So it's a little easy to lose kind of place and kind of go, what is this? But this is definitely, probably for some time, the proof that's going to be the most like twisty, turny, and a lot of little details to keep track of. From this point forward, there's going to be a lot more, especially when we get the linear mappings. It's going to be a lot of just like unraveling definitions. This is definitely a proof that goes a little bit beyond that. has a little more substance to it than just we set up nice definitions and everything works. But anyway, now that
Could
we've
you
proven this,
maybe could you maybe re-emphasize the significance of the proof, or like uh,
uh,
what its implications are, like how we'll use it going forward?
yes. So the main thing, like I said, the main power of this, now that we've got the proof done, so we have access to this theorem, and the key thing, the main thing we're going to use here is this specifically. Right. So the significance here is that now I know that if I have a finite set and I look at its span, the number of linearly independent things in there can never exceed how many things were used to create the span. So the real significance here is that now in, for example, R3, I can't find 4 distinct elements of R3 so that the set formed by them is linearly independent. Scientific exchange assures us that that cannot happen. So
Okay,
yeah,
that's
that's
helpful. Thank
yeah,
you.
that's really what we're going to use this for. This latter chunk of the proof we're basically not going to use. It's just needed to get the first part to work the way we want it to. This sort of like given a set that spans, you can throw out the terms and use these linearly independent things to create the span. Yeah, it's true, but it's not really useful. The real useful thing is this part right here. Right? We were just trying to prove n was less than m, but like actually getting to it required like a bunch of extra junk to get there. So now that we have it, now we can really get some stuff going. All right. So the first thing to note, exactly what I just said. If I am in a vector space and I have finitely many things, and then I look at finitely many things in the span, where the number of things in the span exceeds how many were used, then this set must be linearly dependent. So, for example, or now for the proof, sorry. Just quick proof here. This one's really easy. If this was linearly independent, then Steinitz exchange would force m to be less than or equal to n, because it's right, because Steinitz exchange says that if you have a distinct list of a linearly independent set contained in the span of a finite set, you cannot exceed that. So this immediately now gives us a super easy way to detect linear dependence, especially in the setting of Rn. For example of that, I got more going on. Oh yeah, there you go. Yeah. So as a corollary to that, if you were an Rn and you've got a list of m things, that must be linearly dependent. Right? By Steinitz exchange, we know this has to be the case. Rn is spanned by n things. There cannot be m linearly independent things. They must be linearly dependent. Always, no matter what. So if we're in R2 and I have 3 things, like, oh, I don't know this. And again, very creative. 1, 2, 3, 4, 5, 6. Right. Linearly independent. No, the complete opposite. Oops. Let's let's fix that. All right. Boom. Okay. So we now know, right? For example, in R2, if I take 3 things, I don't care what 3 things you picked, they have to be linearly dependent. Always, no matter what. Right. And at first glance, right, there's nothing seemingly incorrect about these 3. There's nothing clearly like, oh, they're all scalar multiples of each other, or one of them is 0. Right. It passes the first couple of hurdles. Right. This is now saying that there is some scalars A, B, and C, so that they're not all 0, and this has a solution. And specifically, one that works is -1, 2, 1. There are infinitely many. So this is really the power now of the Steinitz exchange model. This is really how we're going to repeatedly use it, because we now know if you are in R7, there is no more than 7 linearly independent things. So, for example, in R2, well, we know of 2 elements that are linearly independent. As we're about to now prove, finding any 2 linearly independent things gives me a basis in R2. So there's even more consequences to the Sandwich Exchange limit. So now we know that in a set that is spanned by finitely many things, you cannot expect to find any more linearly independent things. So in R5, the best you can hope for is 5 linearly independent things. And as we're about to see now, 5 linearly independent things guarantees that it's a basis. So if you're spanned by finitely many things and you find that many linearly independent things, it must be a basis. So, for example, in R3, if you find 3 elements and they're linearly independent, they must automatically span. That is amazing. That is so powerful. So I don't need to prove that they span. I now know by Sandwich Exchange they must span. There is no choice. So let's prove this. So again, all we need to verify is that y v is spanned by the y's. The y's are linearly independent. So how are we going to tackle this? Well, remember, if you don't span, I can always enlarge my linearly independent set. But we're in a set that's spanned by n things. I can't have n plus 1 linearly independent things. Boom. It's got to span. You better listen. If you don't think this is the tightest shit, this proof is so beautiful. It's so nice, and it's so powerful. This tells us so much now, and we just putting in the work to get that Sandwich Exchange limit proof, which I know is not the nicest proof ever. The consequences of that now, right? This is amazing. Because constructing bases now in R3, which, as we will see once we get matrices going and talking about how they're related to linear systems, generating solutions to linear equations now is like, it's for free. Everything that we want now, we basically got proven, and it's so good. And this proof is so slick. Like, there's a talk a lot in math classes where we talk about like mathematical beauty, like a proof being really beautiful, or like math like being really like amazing. This right here, this is a proof. Like, I hope you feel it like deep within your mathematical soul. Like, it should be warming your heart. You're like, oh, this is nice. Not only because we're going to see this as massive applications later on, but just as a proof, it's so 10 out of 10. All right. That being said, let's talk about that a little bit more. This now tells us that to create a basis for Rn, just find n linearly independent vectors. So, for example, the set 1, 2, 3, 4, 5, 6, 7, 8, 10, you can calculate that this is linearly independent. So hit it with some scalars, make the linear combination, set it equal to 0. You can prove that all the scalars have to equal 0. It takes a little bit of work, but it's not impossible. And it's got exactly 3 elements. As we just proved, R3 is spanned by 3 things. So any 3 linearly independent elements must be a span. So I now know that I don't care what you pick in R3. Everything in R3 is a linear combination of these. I don't know what the scalars necessarily are, but I know that I can always solve that question. So before going in all guns blazing, I know there is an answer. And in fact, we know it's even better since it's linearly independent and it spans the set. Not only is there an answer, but the answer will always be unique. There is exactly one dragon that needs to be slayed, and that is a much better situation than infinitely many Schmaugs. All right, nice. Let's push it even further. That is a linearly independent subset of R3. It's got 2 linearly independent elements. If you wanted to turn this into a basis, and right now we don't have the tools explicitly to know that this can't be a basis, right? We are going to prove that every 2 bases have the same number of sets, the same number of elements in a little bit. So we would know this couldn't be a basis. So it couldn't span. But if you wanted to turn to a basis, that would mean you would need to only throw in one more thing that keeps it linearly independent, like you had to do in problem list number 2. So, for funsies, the obvious one is like a 1, 0, 0, but 1 square root of pi is 0, that works. Square root of pi is a fun number. That's got, so you can verify that this is still linearly independent. Hey, it's an R3, and there's 3 distinct things, and it's linearly independent. It is a basis. So everything in R3 can be written as a linear combination of these. I don't know what the linear combo is, but I know it's out there, and furthermore, for any element of R3, that linear combination is unique. All right, so we now know, right, a lot of stuff now about R3, R4, all of Rn. Being able to write elements as linear combinations of linearly independent things, we now have a real solid answer to that, about when it's possible, and when it is possible, when it ends up being unique. Right. So again, keep in the back of your mind, our goal is to talk about how this is all going to relate to data fitting, something we do not just in mathematics, but in all other fields of study. This is telling us something about when we have existence, and furthermore, when the existence is guaranteeing uniqueness. The non-existence case, we'll get to that in a minute. It does that on purpose, yes. All right, cool. All right, so that being said, like I noted here, we don't have anything right now telling us that this couldn't be, no, actually, no, yeah, we know this can't be a basis, actually. Actually, yeah, wait, no, you know this can't span. If this spanned the set, that would mean R2 can have 3 linearly independent elements, but we already know it does. So actually, yeah, you know this doesn't span at this moment. Nice, yeah. So actually, yeah, in the finite case, we actually now know that the only way you could possibly have a basis is with n elements. Yeah, cool. So we'll do one better. All right, anyway, so the last thing we want to prove now is that every 2 bases have the same number of elements in them, and the way we're going to get there is with something called the dimension theorem. And now here I want to scream about our textbook for a little bit. Again, your textbook is something they call the dimension theorem, but what they're talking about is the rank nullity theorem. Nobody calls the rank nullity theorem the fucking dimension theorem. No person calls it that. It's the rank nullity theorem. Dimension theorem is so vague, it doesn't tell you what's actually going on with that theorem. So you never call it that. So infuriating. I hated seeing that. Because to me, if you're going to call something the dimension theorem, if you're going to call anything the dimension theorem, it's this result, right? Which says that if you have a set that spans a vector space and you've got a linearly independent set, the linearly independent set cannot have more elements than the set that spanned it, right? Steinitz exchange is the finite version of this, but it turns out it's true in general. And if you're going to call anything the dimension theorem, it should be this. Because this puts a restriction on, like, dimensionality. And even then, this is pushing it. You really shouldn't call this a dimension theorem. There's enough things in math that are called dimension that dimension theorem is still really vague, and you could be referring to, like, who knows what. So I want to stress your book calls the rank nullity theorem the dimension theorem, and that's dumb, and I'm not a fan of that. And I know I just sweared about people calling the rank nullity theorem the dimension theorem. When I met with Professor Weber at the beginning of the semester, he called it the dimension theorem, and I didn't correct him or anything, because I respect him a lot. But in the back of my head, I was screaming, I'm like, "You asshole! Why'd you call it?" Anyway, all right. So this is sort of the last technical proof, and this is going to be another proof, sort of. So what are we going to prove? We're going to prove effectively that the Steinitz exchange lemma is true for any set. I don't care if it's finite or infinite. Basically, if a set is spanned by something, the number of elements that spanned it, the number of linearly independent things present cannot exceed the amount in the span. Another way of saying that is that the cardinality of S is less than or equal to the cardinality of E, which hopefully from Math 201, if you've taken it, you know that that means there is an injection from S to E for us, basically, for the number of elements within E is no less than the number of elements in S. So in other words, What we're specifically going to prove is that for any number of things you can find in S, I can find just as many things in E. So specifically, for each X that's in here, there is some finite set so that it belongs to the span of it. Right? Anything in S must be in V, which is being spanned by E. So there's some number of elements E that X is a linear combination of. So X is in the span of that set. So for each X, there's some finite subset of E we can associate with it. In particular, given any finite number of linearly independent things, it has to live in the span of that union. And hey, what do we have? We've got a finite set so that the linearly independent things live in the span. I don't know why this is blank, but it is. So by Steinitz exchange, then, we know that this set has to have at least n things. If it has strictly less, then this is the linearly independent set couldn't possibly happen. It would have to be dependent. Right? So that means that for any number of elements in S, so n elements out of S, we can find at least n elements in E as well. So, in other words, for any number of elements that you can find in S, I can always find at least as many in E. That ensures that the cardinality is less than or equal to it. Now, note that I only worked with finite sets. How do you know this lets you jump over to infinite or uncountable or even worse? Well, you're allowed to do this by something called the marriage lemma. And hopefully it's kind of clear what's happening, right? For any finite number of things in S, I can always find finitely just as many in E. So that just titrates up to infinite sets. That is another result. So like I said, this is mildly hand-wavy. The marriage lemma is another require some sort of axiom of choice nonsense proof. So this is not a proper proof, but it gets the idea across. You can make it more formal by invoking the marriage lemma, but that takes us just like it was like using the axiom of choice to get that every vector space is a basis. This takes us way up the deep end if we're going to really write out a formal proof of it. So we'll just get the main part of it, which is for any number of things in S, I can find just as many things in E. So I don't care if they're infinite or not. That means that S has E has at least as many things as S, not the other way around. All right, so now equipped with that, we now get, finally, given any two bases, they have to have the same cardinality, meaning that they have to always have the same number of elements. And the proof of this is super easy. V is a basis, so that means V spans it. H is linearly independent, so by the result we just proved, that means H cannot exceed V in terms of the number of elements. And similarly, V is spanned by H, and V is linearly independent. So the number of elements of V cannot exceed the number of elements of H. So they must have the same number of elements. Now, of course, here I'm missing some stuff. So specifically, I proved that the cardinality of H is less than the cardinality B. Cardinality B is less than or equal to the cardinality of H. The fact that that means that the cardinalities are equal is something called the Cantor Schneider Benedictson theorem, if I remember the full out. Normally, I just give the credit to Cantor. This is actually kind of a non-trivial thing. Is saying this means that you have an injection, a one-to-one mapping, which we're going to get to those if you know what they are. And you've got a one-to-one mapping in the other direction. That means then you've got an invertible mapping. That's kind of a pain in the ass to prove, but it's true. But hopefully, just the general explanation of what this is. H has no more elements than B, and B has no more elements than H, so they've got the same number of elements. So they have the same cardinality. So now we know that, for example, if you are in R5, anything that's a basis must have 5 elements. If you are talking about, say, the set of polynomials, we know that there's infinitely many elements in the basis for the set of polynomials. Any other basis for that set of polynomials has to have infinitely many, and specifically the exact type of infinitely many. It has to have countably infinitely many. And yes, there are vector spaces that have an uncountable basis, and those are real nightmares. Maybe we'll talk about them. Main thing now, with this in hand, so we've now proven two very fundamental facts about the nature of bases, vector spaces. First of all, every vector space has a basis, and furthermore, the cardinality of any two bases are the same. So in other words, any two bases, there could be infinitely many different bases, but they always have to have the exact same number of stuff in them. So that means that I can define the dimension of a vector space. So when we say the dimension of a vector space, what we mean is the size of its basis. Any two bases always have to have the same number of elements. So when somebody says I've got a 5-dimensional vector space, they mean that every basis for the vector space has 5 elements in it. And so, for example, I can tell you that R4 is 4-dimensional, right? And that goes in line with our usual notion of how we think of dimension, right? We live in 3 dimensions. We're 3-dimensional beings. We perceive 3 dimensions, and that lines up with R3. So our notion of dimension lines up into our definition here lines up with our intuition of what dimension should be. But dimension gets a little dicey in math. So if you want to be very particular, you would call this algebraic dimension. There are fractional dimensions, and that gets into things called fractals, which you've probably heard of. Everybody in math loves them. It's weird pictures. Their dimension gets real hazy. So related to that is actually something called the shoreline problem. Check into that if you're interested. That's some mind-blowing nonsense. But anyway, so in the world of vector spaces, when we say dimension, we mean very precisely the number of things in your basis. So the word dimension has a very specific meaning. It's not just sort of a vague, intuitive idea of what dimension is, and it's got a very precise explanation. Right? Again, that's math, poetry of logical ideas. Right? You have a logical idea of dimension, and now we've got very precise language explaining what that is. So then, right, the poetry part, you've got very precise language that's chosen to elicit emotions, and we got very precise language to elicit logical feelings. That being said, let's remind ourselves of something, that the span of the empty set gives you a set consisting of exactly one thing. We call that 0-dimensional, right? The empty set has no elements in it, so 0-dimensional. So if you ever see anything about a 0-dimensional vector space, which we will have to run into occasionally, that means we're talking about a vector space that is trivial. It consists of exactly a single element. And as we noted, such things exist. They're really boring, but they exist. And right, when you set up a definition, you want to look for extreme things. Here we go. All right. So now we've got a precise definition for the word dimensional. It's the number of things in your basis. And now when we talk infinite dimensional, of course, then you can talk about the various different types of infinity that are out there. We won't get too sweaty about that. If you're interested, I can talk your ear off about that stuff, but let's not. Anyway, we're saying goodbye now, but there's a question that hopefully is burning in your mind. Is there any real difference between R3 and, let's say, a vector space with dimension 3? They're both spanned by exactly 3 things. Any of the 3 things are a linear combination. So if you replace the 3 things with the basis elements of R3, the standard ones, basically looks the same. Right, so for example, the polynomial is a realistic circle too. It really feels like that's just R3 in disguise. And some of you tried to use that, and your problem was, we don't know if this is true yet. Don't do that. So I wonder if there's, like, I don't know, a transformation that respects linear combinations that we're going to talk about tomorrow. Ooh. All right. All right. So with that, we have completed the first part of the course. I'm actually ahead of schedule. Approximately 3 weeks. 3 weeks minus a day. Hold that off. So let's see if we can keep that going. All right, but that's it for today. There we go. So tomorrow we'll start linear mappings. We've now proven a lot of powerful theorems, and so we know a lot of really useful information about Rn. So it's going to be a good time. All right, that's it. See you later.